Good afternoon, everybody. I'm Lorenzo Romanelli, PhD student, University of Pisa, and I'm going to present the work entitled Combined Approach Using Critical Distance Theory and Extreme Value Statistics to assess the impact of surface roughness and pores on the fatigue strength of Inconel 718. The work is the outcome of a fruitful collaboration between University of Pisa, the University of Trento, and University of Parma. As it's well known from the literature, defects such as keyhole, lack of fusion, pores, and surface roughness have detrimental effects on the fatigue strength of AM components. Various techniques are available to model the impact of porosities, such as Murakami model, which can also be used to model the impact of surface roughness. In this work, we proposed a simplified approach combining theory of critical distances and statistics to describe the combined effect of porosities and surface roughness on the fatigue strength of AM components made of an Inconel 718 under different surface conditions. The specimens that were manufactured in this research are presented in this slide. The one on the left had a sharp notch, and it underwent a turning machining operation before fatigue test in the zone around the notch to reduce the impact of surface roughness on the fatigue strength. And this surface condition was named as machined one. And this specimen was only used to identify critical distances, while the specimen in the middle had a blunt notch, and it underwent fatigue test under two surface conditions. In fact, one group underwent turning machining operation in the zone around the notch, while another group was tested in the as-built surface conditions without any surface treatments before fatigue test. The specimens in the machined conditions were used to identify critical distance, while the ones in the as-built conditions were used to validate the proposed methodology. Finally, on the right, we have specimens without any notches. That was tested under in as-built and machined surface conditions, and it was only used to validate the proposed methodology. And the design of the specimens was coherent with the reference here reported for the identification of the critical distance. The specimens underwent an aging treatment coherent with the AMS 5663 to increase the surface hardness with respect to the base material. Then we performed the fatigue test with a load ratio equal to 0. The fatigue limit was fixed at 2 million cycles because of previous research of the group. And after a fatigue test, we started investigating the fractographic analysis to understand the possible reasons behind the fatigue crack initiation. For the sharp machined V-notch specimens, we obtained that the notch was the only responsible for triggering the fatigue crack, while, for example, for the plain as-built specimens, we obtained that the combination between surface roughness and porosities could play a key role in triggering the fatigue crack, similarly to the plain machined specimen and the as-built blunt V-notch specimens. Given the key role of pores, we investigated 2D images obtained through the optical microscope, trying to identifying two key variables of the pores as the pore diameters and distance from the external surface. As it's clear from these images, there was not such high amount of pores because the specimens were manufactured with optimized parameters that were obtained following the Rosenthal solution, and the work is discussed in the reference here attached. And however, even if few, the pores could be located next to the external surface, and the use of these optimized parameters avoided to obtain such a lack of fusion and the keyhole defects. On the other hand, we reconstructed the surface morphology of the specimens through the use of a 3D optical profilometer, which was focused in the highly stressed surface of the specimens. Once the experimental data were collected, we started performing some statistical analysis of the pores, trying to investigate possible correlation between pore diameters and distance from external surface. We started using Pearson correlation factors, which in principle could not be applied because it has strong assumptions behind, such as that the variables have to be normally distributed and that linear relationship must occur between them. Thus, we moved to the use of Spearman correlation factor and Kendall correlation factor. But in all cases, we obtained the low correlation factors, much lower than 0.5. This rigorously does not mean that no relationship occur between the variables, but given the obtained low correlation factors, we analyzed the two quantities separately. In fact, we use a Gumbel distribution function according to the work of Murakami to model the pore diameter, and we use Kolmogorov-Smirnov hypothesis test on various distribution functions for distance from external surface, and we obtained a high p-value, for example, for the exponential distribution function. Once the statistical analysis of pores was completed, we had to identify the critical distance. In principle, we wanted to use a combination between the plain machined specimen and the severe Wu-Notch machined specimen, following the approach proposed by Santus, Taylor, and Benedettii to avoid the identification of the threshold stress intensity factor range, which can be challenging to be identified experimentally. However, this approach could not be applied, given that the pores play a key role in triggering the fatigue crack of plain machined specimen. As a consequence, we use the double notch inversion, which combine the machined, blunt, and Wu-Notch specimens. And in this case, the intrinsic fatigue strength is an output of the procedure, while in the previous case, it was equal to the fatigue strength of the plain machined specimen. This approach is coherent, for example, with other research group for fatigue strength analysis of cast iron specimens. However, also the double notch inversion could not be applied because we obtained that the pores also played a key role in triggering the fatigue crack of machined blunt Wu-Notch specimen. In fact, for example, for the specimen indicated with 1, no pores were detected at crack initiation zone, but for example, for the specimen indicated with 2, pores were obtained near crack initiation zone. So we needed to reconstruct the intrinsic fatigue curve of blunt machined Wu-Notch specimen, and we tried to do this following a simplified approach. In fact, we consider that the specimen indicated with 1, where no pores were detected at crack initiation zone, was the fatigue limit of the intrinsic fatigue curve, and then the rest of the curve was reconstructed considering the assumption proposed, for example, by Juvenal, thus by considering an intersection at 1000 cycles between the intrinsic fatigue curve and the experimental fatigue curve of the blunt Wu-Notch specimen. This assumption could be motivated considering that at the low number of cycles, the plasticity plays a key role in redistributing the stresses that the effects of defects can be considered negligible. So once the intrinsic fatigue curve of a machined blunt Wu-Notch specimen was obtained, it was combined with the experimental curve of severe Wu-Notch machined specimen, and the critical distances were identified. Once the critical distances were identified, we had to obtain the fatigue stress concentration factors provided by the pores and the surface roughness. And we started with the pores. At the beginning, we generated 2 distribution functions, with 2 uniform distribution functions, one for pore diameters and one for distance from external surface. Then we reversed the 2 expressions for pore diameters and distance from external surface, and we substituted the generated uniform distributions. As a consequence, we obtained two data sets of pore diameters and distance from external surface that were used in 3D finite element simulations with some modeling technique. And once the finite element simulations were completed, we identified the nodes experiencing axial stress sigma XX ranged between 90% and the maximum. We extracted radial path and we calculated fatigue stress concentration factors according to line method and point method. And clearly, the node experiencing the highest fatigue stress concentration factor was the selected one, and we repeated the procedure for the other node, the other pores. The same reasoning was implemented also for the V-notch specimen, but in this case, after finite element simulations, we had two stress concentration factors, one given by the pore and one given by the notch. And given that we wanted to obtain the fatigue stress concentration factor given by the only pore, we firstly performed 2D finite element simulations of the only notch, and we calculated fatigue stress concentration factor provided by the notch with the theory of critical distances. Then we came back to the 3D finite element simulation. We extracted the radial path starting from point A, and then we calculated the fatigue stress concentration factor of the only pore by rationalizing by the fatigue stress concentration factor of the only notch. We also performed the 2D axisymmetric finite element simulation for the surface profiles obtained through the optical fluorimeter with some modeling technique for plain as-built and machined specimens and for as-built blunt V-notch specimens. And we extracted radial path starting from nodes experiencing stress concentration. So once the fatigue stress concentration were obtained, we used Gumbel distribution functions to describe their distributions, and we identified the values at 90% of probability. And then we started to performing some predictions. With the fatigue strength, the predicted fatigue strength of plain machined and as-built specimens and of the as-built blunt V-notch specimens was obtained as the ratio between the intrinsic fatigue strength and the product between the fatigue stress concentration factors of pores and surface roughness and 90% of probability. While the fatigue stress concentration, the predicted fatigue strength of the machined blunt V-notch specimen was obtained as the ratio between the intrinsic fatigue strength of the blunt machined V-notch specimen and the fatigue stress concentration factor given by the pore at 90% of probability. And here are the results in terms of predicted fatigue strength and number of cycles to failure. And we obtained that line method provided better and higher accuracy than point method. We investigated the reason behind these aspects, and we motivated this considering the plots of this slide, in particular the one on the left regarding the surface roughness, where it is evident that the point identified by the point method is outside the initial region of with a high gradient provided by the surface roughness. Thus, the point method tends to underestimate the fatigue stress concentration factor provided by the surface roughness, and the point method tends to overestimate the fatigue strength, as explained by the previous slide. Recently, we have also performed further analysis on different types of powders. In particular, we considered one type of powder composed of 50% virgin and 50% cyclone, one kind composed by 50% virgin and 50% recycled. Clearly, it is necessary to use these statistics to analyze the experimental data, given that they are not very much, they depend on experimental facilities, but we would like to overcome the use of distribution functions to analyze the numerical data. Because in principle, if one can generate a very high amount of numerical data, we can use directly the sampling distribution. In fact, for example, for further analysis, we built a numerical function to relate the fatigue stress concentration factors of the pore according to the theory of critical distance to the distance from external surface and pore diameters by simulating set amount of data of approximately 100 or 150. And then we generated a very high amount of data of diameters and distance from external surface through the identified probability distributions on the experimental data. The generated data were substituted into the obtained numerical function of the stress concentration factor. And here are the results. For example, on the left, we can obtain a very high amount of data, use directly the sampling distribution. We are also doing the same for surface roughness. In fact, we built an automatic finite element script to import the surface profiles obtained through the optical profilometer, through the 3D profilometer, then perform the finite element simulation and extract the radial path from points experiencing stress concentration. In conclusion, in this work, we started considering the role of porosities on the fatigue strength of AM components made of Inconel 718 and produced through laser powder bed fusion. We considered pore diameter and distance from external surface. We used extreme value statistic and exponential distribution to describe pore diameters and distance from external surface respectively. And we reconstructed surface morphology through the use of optical profilometer. Then we moved to the identification of the critical distance through the double notch inversion, and we calculated the fatigue stress concentration factors provided by pores and surface roughness once finite element simulations were completed. Then we combined the two effects in a simplified way by multiplying the fatigue stress concentration factor and 90% of probability. We obtained a higher prediction accuracy of line method rather than point method. And I would like also to thank the National Project Repowder, which have enabled us to perform this analysis, which is enabling us to continue the investigations on different types of powder. I would like to thank you for your attention, and you are interested in this work we recently published in the International Journal of Fatigue. So thank you.